This question came from the 5.1 worksheet number 2, and it's problem number 5 there. They've given you a function. You'll notice it's linear. Y is equal to negative x plus 5. They've given us an interval here from negative 7 to 5, and they've asked us to approximate the area underneath this curve right here using inscribed rectangles, and they specifically told us they wanted 4 subintervals. So that's how I came up with the I4 here. Now, to be honest with you guys, I thought this was a really disappointing problem, and I'll show you why here in just a second. I think inscribed rectangles could be really, really interesting, and I think on this problem it just kind of stinks. Let me show you what I mean here. So we're dealing with the function here of y is equal to negative x plus 5, and I think I put that in a dumb spot now that I look at it, so here we go. That function right there has a y-intercept of 5, so I'm just going to randomly go right about here and say, okay, that's 5, and it's got a slope of negative 1. So my y-intercept puts us right there. A slope of negative 1 means we're going to be drawing something that looks like this, and it's going to go up in the other direction like that, of course at a 45-degree angle. And the reason I move this graph around, I can pretty much ignore the first and the fourth quadrants because my interval is just from negative 7 to negative 5. So, okay, that really just means I'm working to the left here. So, trying to get my spacing right, that might be negative 5, and I know I'm exaggerating this, guys. That scale isn't very good, but there's negative 7. So I'm going to draw a vertical line segment right here at negative 7 all the way up to the curve right there, and I'm going to do the exact same thing here at negative 5. Those are pretty straight lines I just drew. I'm impressed. And what we are trying to do, guys, is approximate that area underneath that curve using inscribed rectangles. Now, I should point out here, I almost caught myself making a mistake. The directions specifically say on this problem here, guys, that we are to approximate the area under the curve using 4 inscribed rectangles. I bring that up because this region right here is a trapezoid, because this is a linear function. I don't actually need an approximation method right here. I know the formula for area of a trapezoid. Hopefully you guys do too, or you could maybe deduce it by cutting this thing up into a triangle and a rectangle. So we could actually find the real answer here, but I'm following my directions which say to do I4 here to come up with it that way. Okay, so how are we going to do that, guys? We are going to partition this interval into 4 subintervals, which means I'm going to cut it in half right here, and that's going to be at negative 6, and then I'm going to cut it right in half here and here as well. So we've created 4 subintervals. 1, 2, 3, and 4. And now we have to build a rectangle off each one of those bases right there. But the question in 5.1 is, what kind of rectangles are we being asked to build? There are left endpoint rectangles, right endpoint rectangles, midpoint rectangles, and this one, inscribed rectangles. So what inscribed means is that all of the rectangles in an inscribed approximation absolutely must stay below the curve. So don't write this down. I'll show you, for example, on subinterval 2 that a left endpoint approximation, which would look like that, is no good because it gives me all of this extra area right here that's above the curve, and you're not allowed to do that in an inscribed rectangular approximation. So this problem, because the curve is strictly decreasing, this problem gets pretty boring. We are just going to be doing right-hand rectangles here, guys. This is what it would look like on subinterval number 1. Here's what it would look like on subinterval number 2. Here's what we would look like on subinterval 3. Gotcha. And subinterval 4 is going to go here and look like that. Okay? All right, so we're going to be dealing with this one right here, and I'm going to write something here, but I want to caution you guys, in this particular problem, the approximation of I4 would be exactly the same as the approximation of R4. But that will not be true in every single problem, guys. If the curve was actually increasing from left to right, then we would need to do left endpoint rectangles in order to stay below. And what would have been far more interesting is if, and this is where this problem disappointed me a little bit, what if the function had a change in behavior a couple of times? And now, if I wanted to keep this thing entirely below from here to here, I'd have to do a right endpoint rectangle to stay below the curve right there. But on another subinterval, maybe from here to here, I'd have to do a left endpoint approximation to stay below the curve right here. And the really fun part is that, okay, if that was subinterval number 1 and this was subinterval number 3, and I know my spacing isn't very even, but let me call this subinterval number 2, here, you'd actually have to find the minimum value of the function on this interval and let that be the height of your rectangle. So inscribed rectangle problems can be really, really interesting, and they can make you think hard about what type of rectangle you need to be drawing in each case. Okay, so what I've just sketched here in green would be an example of that. Unfortunately, for me anyway, because this problem is simply, strictly decreasing right there, this statement happens to be true on this problem, and we can just approach it this way. So anyway, I think this one's a little dull, but that's just me. So I4 is equal to, all right, guys, we are dealing with regular subintervals right here. So that means that we can find delta x and then pull that out in front. Now, if you remember your formula, delta x is going to be b minus a all divided by n. Your b value is always the right endpoint of the function, -5 in this case, minus a, the left endpoint. So that's going to be a plus 7, and n, they told me right here, n was going to be 4. So -5 plus 7 is 2, 2 over 4 is 1/2, and I think you could probably tell that's the width of all of those rectangles then. Now, because the subintervals are regular, I'm going to pull that delta x of 1/2 all the way out in front. And now I'm basically factoring it out. And now all I'm going to do is add up the heights of all of these rectangles here. Okay, so the height of the first rectangle would be f of, and again, guys, we need the right endpoint of that first subinterval right there. So that is going to be -6.5. Then the height of the second rectangle comes from right here. That would be f of -6. Our third subinterval, its right endpoint is there at -5.5. And the last subinterval has a right endpoint there, so that'll be plus f of 5. Now, one thing I always want to point out, and I always want you guys to notice, look at the gap, the jump right here between all of your x values. That should equal this delta x right here. And even though I wrote it inconsistently as a mixed number and then a decimal here, yeah, that same thing is happening. Okay, gotcha. Also, poor notation on my part. I shouldn't have called these things f if I didn't call the original function f of x. So anyhow, here we go. We've got a 1/2 then times, here we go, f of -6.5. So that is the opposite of -6.5, 6.5 plus 5. That's going to be 11.5. Okay, f of -6, 6 plus 5 is 11. Then f of -5.5, 5.5 plus 5 is 10.5. Gotcha. And then plus f of 5, that would be, I just realized I forgot my negative right there, sorry. And that becomes 5 plus 5, which is going to be 10. So these four values right there represent the heights of the green rectangles that we have drawn right here. Even though my figure isn't really to scale, that seems about right to me. Okay, so where are we at then, guys? This is going to be a 1/2 times, well, 11.5 and 10.5 is going to make 22. The whole numbers, 11 and 10 make 21. 22 and 21 makes 43. And half of 43 should be a 21.5 for our answer here for problem number 5 on the 5.1 worksheet number 2.